Good morning, everyone.
Good morning, sir.
Good morning, sir.
Good morning. Are you able to see the screen?
Yes, sir.
Right. Okay. Fine. So in the previous class, we started with the collector feedback amplifier, right? So this is the circuit of collector feedback amplifier. On the input side, as well as on the output side, you have had two capacitors, right? Ci and C naught. Okay. Since we are going for AC analysis, so what we did was we short-circuited Ci as well as the output coupling capacitor C naught. Okay, because for AC signal, capacitor behaves like a short circuit equivalent. Okay, and you had also, had the bypass capacitor. Again, this bypass capacitor, we are going to replace it with a short circuit equivalent, and thereby, short circuiting the emitter resistance Re. Okay, and taking, that into consideration, we constructed the Re model of the circuit, and this is how the Re model looks like. Okay, it almost remaining the same, okay, as compared to emitter bias circuit as well as voltage divider bias circuit. The major difference over here is that the presence of RF, right? Because between collector and base, there is a direct interaction through the feedback resistor RF. So taking, that connection into consideration, what we have done is between base and collector, we have placed a feedback resistor RF. So remember one thing, this capital RF is basically the biasing resistor itself. All right, fine. So yeah, so these many things we had drawn in the previous class. Okay, so let's continue now. Okay, so we will mark the performance parameters. Okay, so on the input side, when you look into the network, you get to see Zi there. All right, and on the output side, when you look into the network, you are going to have Z naught. Okay, and AI and EA naught, sorry, AV can be computed accordingly. All right, fine. So what we will do is we will try to find first Zi. Okay, Zi, the input impedance. Okay, now the input impedance Zi cannot be judged just beta Re, right? Because with beta Re, you also have RF connected. So, when you look into the network, it is pretty obvious that beta Re and RF, they are neither connected in series nor connected in parallel. Okay, so you have a kind of peculiar arrangement of resistance. So in order to find Zi, what we have to do is we have to apply the circuit analysis technique. All right, so what we will do is we will try to apply nodal analysis. So let me write apply nodal analysis to determine, okay, current I dash, where I dash is the current which flows through the feedback resistor R. All right, so let's try to determine I dash. Let's see what we get. So let's write I dash is equal to, okay, as per nodal analysis basically follows Kirchhoff's current law, right? I is equal to difference in potential divided by the impedance. So what is I dash? So I dash is nothing but, potential difference across RF, okay, divided by the resistance value. So across RF, you have two potentials coming in. At the collector terminal, you have V naught, and at the base terminal, you have Vi. So the difference in potential going to be V naught minus Vi. Is that right? Divided by the resistance Ra. Okay, so let's take it as equation 1. Okay, also you can write V naught is equal to, okay, so you see here we have taken the standard output voltage convention as lower side negative, upper side positive. but the actual current I naught, when it flows through the resistor, RC, produces output voltage, sorry, in the flipped manner. So V naught can be written as minus I naught into RC. Okay, so that will be the equation 2. Okay, and you can also apply, KCL. Okay, I'll write here. Apply KCL at collector node. Okay, when we apply KCL at collector node, what do we get? Input current is, incoming current is I naught, and outgoing currents are IC and I dash. Okay, so I naught is equal to outgoing currents, I dash plus IC, which is nothing but I dash plus beta IB, because IC is beta IB. Okay, let's take it as equation 3. Okay, I hope you are taking down these equations, simultaneously. Okay, all right. Okay. Okay, but on the output side, see, if you were to compare the current levels, okay, we see that your beta times IB, okay, beta times IB is very large in comparison with I dash. So on that note, what you can write is I naught, approximately equal to beta IB. Okay, so this reduction greatly helps in the further analysis. So we can slightly, reduce the complexity. Okay, on what note? On the fact that your beta IB, which is IC, so IC is very large in comparison with I dash. Okay, because this I dash flows through RF, and RF value is generally very high. Okay, because this RF also, helps in keeping base current under check. Okay, so that's the approximation what we follow on the output side. So I naught becomes beta times IB. Okay, all right. So therefore, okay, what you can do is substitute 4 in 2. Okay, what I'm doing, I'm substituting 4 in equation 2 so that I can get an expression for V naught. So what do we get? V naught is equal to minus, okay, against I naught we have beta IB into RC. Okay, say equation 5. Okay, equation 5. Okay, also from the input side, you can write an expression for IB. From the input side, IB can be written as, from the input side, IB can be written as, okay, what you can write for IB? Okay, so IB is this, the current flow through resistor beta RE. Okay, so across beta RE, what voltage is coming? VI is coming, right? Because base to ground voltage is same as, voltage measured from this node to this node. Okay, this node is your base node, and this node is your ground node. So your base current IB can be written as voltage divided by resistance. So that is VI divided by beta RE. Okay, say this is 6. So now what you can do is, you can again substitute expression IB in expression V naught. So substitute equation 6 in 5. Okay, it's something like, chain reaction we are doing. One after the other, we are we are going on substituting. Okay, so that becomes minus beta, okay, into IB. So against IB we have VI divided by beta RE into RC. So beta gets cancelled. So the output voltage expression, you will get it as the resistance ratio RC by RE into the input voltage VI. Okay, VI. So say this is equation 7. Okay, now what we have done is we have found some alternate expression for V naught. Okay, so that you will be able to substitute that V naught in your first equation. Okay, your first equation is I dash equation. Okay, so all right, so substitute equation 7 in equation 1. Okay, so equation 1 is I dash, so I dash is equal to let me write V naught minus Vi divided by Rf. Okay, which is equal to, let us split up V naught by Rf minus Vi by Rf. Okay, and that is equal to, you can write the expression for V naught here. Okay, what is it? V naught expression, negative Rc by Re, okay, into Rf. Okay, since there is no space in the here, let me write. So I dash is equal to V naught. V naught is minus Rc by Re into Rf, because Rf is in the denominator, into Vi minus Vi by Rf. Okay, which is equal to, okay, you see here, let me mark the similar terms Rf. So what you can do is you can keep out 1 by Rf, as well as you can keep it outside the bracket, the Vi term as well. So if you do that, what you get is 1 by Rf. Okay, open the bracket. Okay, and what I'll do, I'll keep Vi also outside the bracket. So basically what you are doing is, let me take out the negative sign so that this term I can write it as unity. Okay, so what you have done is you have taken out minus Vi divided by Rf outside the bracket, right? So minus 1 by Rf is here and Vi is here. So effectively inside the bracket you will have 1 minus, okay, so this becomes plus again because there is a negative sign, Rc divided by Re. Okay, so basically you will get this resistance ratio added with unity. Okay. Okay. So fine. So let's keep it as equation 8. Okay. Next, what we can do is, yeah, we can write the expression for Vi, because in the end we have to take out the expression Vi by Zi. Sorry. The whole idea is to take this expression, okay, Vi by Ii. Okay, all right. So we also have, okay, I dash. Okay, just a minute. Yeah. Vi greater than, right? So Vi, we can write it as Ib into beta R. You have already seen, right? Let me just give some trace where I have already discussed about this expression. Vi is equal to Ib into beta R. Here it is. Okay. If you cross multiply, you will get voltage as current into resistance. Okay. So in bracket, let me write from equation 6. Okay. Fine. Or Vi is equal to Ib. Okay, Ib. What is Ib here? What is Ib here? Can anyone tell me? Can anyone tell me what is Ib here? On the input side, you apply KCL at base node. That will help you in finding out, Ib. So at base node, two currents are entering. II is entering and I dash is entering, and outflow current going to be base current Ib. Okay, so what we can do is Ib is equal to, you can write I dash plus IL And how did we get this? So to get this, you need to apply KCL at node B. Okay, at node B. So let me write IB as I dash plus II into beta I. Okay, or let us split the terms. So it is I dash into beta I plus II into beta I. Okay, or Vi is equal to II beta RE, let me keep it as it is, II into beta RE, okay, plus you have I dash into beta RE. Okay, we have already written an expression for I dash. Okay, so here let me write, where somewhere here, okay. Substitute I dash from, okay, you had written an expression for I dash, right? Yeah, from your output circuit. See here, equation 8. Substitute I dash from equation 8. Okay, let me show this equation. Your equation 8 is here. Okay, so let's substitute that equation. Negative, right? So negative 1 by Rf into 1 plus Rc by Re into Vi, okay, into beta Re. Sorry, not this. Not this. This beta Re, because I'm, yeah, term which is associated with I dash. Okay, so the Vi into beta Re. Okay, fine. So what you do now is that you collect the like terms together, in the sense you have one Vi term here and you have the second Vi term there in the right hand side. So what you do is you bring this Vi term onto the left hand side so that you can group the like terms together. So this is Vi. When you take this on the left hand side, it becomes plus. So 1 by Rf, okay, into 1 plus Rc by Re. Okay, so what I've done is I've taken capital Re. It should have been small Re. Okay, into beta Re. Okay. Since Vi is common, I can reduce one step. We write 1 plus something. Okay, this let me take Vi. Okay, is equal to II into beta Re. Okay, II into beta Re. So now you can take out the ratio. Okay, now let us take out the ratio Vi by II. So what do we define Vi by II as the input impedance Zi. So Vi divided by II is equal to beta Re on the numerator, and this big denominator you will have 1 plus 1 by Rf into 1 plus Rc by Re, okay, into beta Re. Let me keep this beta Re over here itself. Okay, so this is your expression for Zi. Okay, so as expected, you will get kind of crazy expression. Okay, so Zi is equal to beta Re divided by 1 plus beta Re divided by Rf into 1 plus Rc by Re. Okay. Okay, fine. So if you want, you can go for approximation. There is no, what you say, hard and fast rule that you have to go for approximation, but I can tell you what kind of approximation I'm trying to propose. Okay, now if you compare this particular ratio, okay, 1 plus Rc by Re. Okay, so 1 plus Rc by Re is approximately equal to Rc by Re, simply due to the fact that this ratio Rc by Re is very large compared to the unity, right? So it's something like a drop in ocean it becomes, hence 1 plus Rc by Re, you can simply take it as RC by RE. Okay, taking that into consideration, your input impedance Zi becomes, beta RE divided by 1 plus beta RE divided by RF into RC by RE. So RE gets cancelled. Hence, you are left with Zi is equal to beta RE in the numerator. Okay, and in the denominator you have 1 plus beta into RC divided by RF. Okay, into RF. Okay, or if you were to take beta outside, so what I will do, I will take out beta as the common factor both from the numerator and the denominator. So in the denominator, when I take out beta outside, so this becomes 1 by beta, and this becomes RC by RF. So beta cancels. So approximate expression, you will get it as Zi is equal to RE divided by beta inverse, that is 1 by beta plus RC by RF. Okay, C by RF. So this is my approximate expression. Okay, and this is my exact expression. Okay, so this approximation is optional. Okay, if you get the trick, you can provide. If you don't get the trick, it's okay, you can leave it off. Okay, that's fine. Okay, so this is your input impedance. Did you understand? So here the whole idea is to start from output side. Okay, so I'm telling you the algorithm for solving this particular amplifier circuit is that start from output. Okay, and write down I dash IC plus I naught. Okay, then substitute, I naught is equal to what, then IC is equal to what, etc., etc. Okay, then go to input. Okay, and write expression for IB. So IB is equal to II plus I dash. So here substitute I dash from output side. Okay, and third step is to take out the ratio VI by II. So this is the algorithm basically. All right. To solve, collector to base amplifier circuit, you need some practice. Okay, if you have practice, you will find it very easy. Okay, you may have to practice for once or twice. Okay, just remember one thing. Till now we have just solved Zi. That's all we have solved. Okay, now let's go to Z0. Okay, by definition, Z0 is V0 by I0. Okay. Now, what we will do is that we will apply, okay, to find Z0. Okay, once again, you can make out that in the circuit, you can clearly observe that Z0 is not RC alone, right? Because there is a resistor, RF, which is also connected to the output side. Right, because you can see that RF is also connected to collector side, and to the same collector we also have a resistor RC. So directly you can't say Z0 is equal to RC. Okay, instead you need to find Z0 through the circuit analysis. Okay, so let's find Z0 through circuit analysis. I hope you understand why am I considering why I'm not considering Z0 as RC, because to the same collector terminal, we have resistor RF connected as well. Okay, so to find Z0, what I will do is I will apply Thevenin's theorem. Okay, apply Thevenin's theorem. Okay, so the Thevenin's theorem will help me in greatly reducing the circuit. So as per Thevenin's theorem, what you do is you set, okay, this is not delta, you set Vi is equal to 0. Okay, what do you mean by set Vi is equal to 0? Short circuit input source Vi, right? So SC, the input source, so that means to say Vi, you are setting it to 0. Okay, and due to which what happens is that control source beta IB, is made 0. That's because you will open circuit current source, short circuit voltage source, open circuit current source. Now, when I apply Thevenin's theorem, okay, what I get is the equivalent circuit. Okay, so observe carefully. Your Vi, you are setting it to 0. So that means to say you have a direct short at the input terminal. Okay, and then across Vi, you have beta RE, correct? And this is your base terminal. Okay, and then you have your feedback resistor RF, and here is your collector terminal, and collector to ground. Okay, you have had a controlled source, but that controlled source is reduced to 0. Okay, and then you have the resistor, collector resistor RC. Okay, and that's your output impedance Z0. Okay, so this is your I0 and this is your Z0. Okay, so this is what the equivalent circuit looks like. Okay, now we'll have to observe, certain happenings in the circuit. For example, if you look at this particular connection, okay, if you look at this particular connection, you observe that across beta RE, you have a short circuit, right? That's because you see this node is connected to base, okay, and the same node is connected to ground. That means to say your base terminal is directly held at ground terminal. That means to say short circuit is present across beta RE, okay, due to which what will happen is, okay, therefore base is at ground potential. So this base terminal is held at ground potential due to the short circuit phenomenon introduced at the input source Vi. Okay, taking that into consideration, what happens is that, okay, let me rewrite the circuit. So this entire circuit which is present within the shaded region, I'm going to replace it with a short circuit. So base is at ground potential. Okay, so this is your base terminal. Okay, what I will do, this is my base terminal. I will keep it at ground. Okay, so this same base is then connected to RF as well. So let me connect RF here. Okay, and the other end of RF is connected to collector, and the collector terminal is also connected to RC. Okay, and other end of RC is grounded. Okay, and this is your Z0. So what is Z0? Z0 is basically a parallel combination of RC and RF. So it is RC into RF divided by RC plus RF. So that's your Z0. Okay, parallel combination. Fine. Next, we have the third performance parameter, voltage gain. AV. Okay, by definition, voltage gain AV is V0 by Vi. All right. Okay. Where V0, okay, V0 can be written as minus I0 into RC. Okay, I think I have already told you this I dash. sorry, I naught is basically beta IP plus I dash, right? We have already seen that I naught is beta IB plus I dash here. Main circuit, let me show you here. See, incoming current is I naught. So if you apply KCL at collector node, I naught is equal to IC plus I dash. Okay, that's what I have written. Okay, so this is IC. So IC is beta IB, and you know, approximately you can write this as beta IB, which is IC. Okay, that's because I dash is very small. I hope you remember this particular thing when I explained while calculating Zi. Okay, so that's your V naught. Okay, fine. So you can write V naught is equal to, you know, I naught. So I naught is basically beta IB. So it is negative beta IB into RC. Okay, and then you have VI. Okay, so what is VI? VI, you can write it as IB into beta RE. Okay, IB into beta RE. Therefore, your voltage gain AB is equal to output voltage, which is minus beta IB into RC divided by input voltage, that is IB into beta RE. Okay, so that is equal to, okay, so IB gets cancelled and beta gets cancelled. So your voltage gain becomes the ratio of collector resistance to AC emitter resistance RA. Okay, so voltage gain is minus RC by RE. So you can say that, you know, similar to emitter bias and voltage divider bias with bypass capacitor. Okay, so it's a similar expression. Okay, so that's your voltage gain. And finally, you have your current gain AI, which is I naught by II, which is V naught by Z naught into you know, Zi by Vi. So you have this ratio, you know, V naught by Vi. Okay, so this is minus, okay, because output voltage is negative here. So this becomes voltage gain times the input to output impedance ratio. So that's your AI. Okay, so remember one thing, your AI expression, you know, it remains the same. It is voltage gain times the impedance ratio measured from input impedance to output impedance. So that completes the analysis of collector to base bias amplifier. So 4 performance parameters, all 4 have been determined. Here, one takeaway, what you have to understand is that the analysis of Zi is not straightforward. It requires some amount of understanding as well as hard work. All right, so you have to practice Zi expression. I hope you will do it. Okay, fine. Is it clear? Can we take up the second circuit?
Yes, sir.
Okay, fine. So second circuit, what we have for the day is the emitter follower. It's a very interesting circuit. Emitter follower. Okay. Remember one thing, this emitter follower can be constructed either from voltage divider bias, or it can also be constructed from emitter bias. Okay, either voltage divider bias or emitter bias. Only the difference is that in case of emitter bias, we take the resistance RB. In case of voltage divider bias, we take it as RTH, where RTH is the parallel combination of R1 and R2. Okay, so in both ways, you can get the working of emitter follower. But in the exam, what they ask, we don't know. Okay, so what I will do, I will do an emitter bias circuit for sorry, emitter follower circuit for voltage, emitter bias basis. Okay, so I will do emitter follower with emitter biasing network. Okay, you can try out for voltage divider bias circuit as well. It gives the same results. Okay, all right, fine. So what is this emitter follower? Okay, I'm not calling it as an amplifier. In the previous circuits, everywhere I used to call it as voltage divider bias amplifier, etc., etc. So here I'm not calling it as an amplifier because of a particular reason. So your emitter follower is not an amplifier. Okay, your emitter follower is not an amplifier. If it is not an amplifier, then what it will do with the signal? So this emitter follower gives voltage gain approximately 1, in the sense, okay, let's say this is your emitter follower EI. If you give VI, say having a maximum voltage of 1 volt, you will get output with a maximum voltage of 1 volt. So basically, your emitter follower is equivalent to 1:1 transformer. Okay, in transformer, you had seen that the moment when you take or keep the ratio N2 is equal to N1 is equal to N, your transformation ratio K becomes 1. So when transformation ratio K becomes 1, what happens is that V2 is basically K times V1. So V2 becomes V1. So, it is kind of similar. So you could say that, your analogous device for a transformer in AEC is the emitter follower circuit, because the gain for emitter follower is 1, and for 1:1 transformer, the transformation ratio is 1. So this voltage gain, can be compared with the transformation ratio. Okay, all right. Then why do we use that 1:1 transformer? Can anyone tell me? In transformers, you must have also studied that 1:1 transformer is used for isolation purpose. Isolation purpose. That is to separate out the high power input circuitry from the low power output circuitry. So that is one major application of 1:1 transformer. Okay, and the second very important application is impedance matching. Impedance matching. Okay, so that is what this emitter follower circuit gives. Impedance matching. Impedance matching. I think I have told you about impedance matching. Okay, so this impedance matching is basically a technique in which the load impedance is matched with the source impedance. Okay, so by doing impedance matching, what you can ensure is that the maximum power delivery from source to the load. If you are able to deliver the maximum power from source to the load, then the signal reproduction becomes proper, and you will have a very good behavior, okay, in terms of audio quality, etc., etc. Okay, so why this impedance matching comes into picture? Let me tell you with a small example. Okay, consider an audio amplifier. Okay, say this is my audio amplifier. Okay. Where do you find this audio amplifier? This audio amplifier may be sitting within your cell phone, right? So this is your audio amplifier. Okay, I will write, this is your mobile phone's audio amplifier, right? Now this audio amplifier, okay, will have some input and it will have some output. Okay. So input, normally it could be the MP3 tracks or whatever, the streaming music, what you are pushing into the audio amplifier. So MP3 track, for example, is your input, all right? and it will have some gain AV and it will give you some output V0. Okay, that's fine. That's how it works, right? You give some input and it gives some output. Okay, what is there within the audio amplifier? Let us not worry. Some internal circuitry it is consisting of transformers, etc., etc. All right. So output. Now I am interested in the output impedance of audio amplifier. Okay, this is Zi and this is Z0. Now, in the previous class, you have studied different amplifiers, right? You had studied voltage divider bias based amplifier, emitter bias amplifier, etc., etc. Now, this output impedance for a typical audio amplifier generally varies. Okay, so this Z0 normally comes as RC divided by RE, and generally this ratio comes in kilos of ohm. Okay, example, let's say RC is your, sorry, this is voltage gain, right? I'm so sorry. This is voltage gain. I shouldn't take Z0. Z0 is normally, okay. Z0 is, say, RC. Okay, say Z0 if it is RC, it is in kilos of ohm. Okay, and to this output, what are you connecting? You will connect 3.5 mm jack. Okay, and this is your headphone. Okay, this is your earphone. I have told you in the beginning. So this earphones or headphones, whatever you are using, will have an impedance either 32 mm. Sorry, that's the driver. Sorry, either 32 ohm or 16 ohm. So that's the impedance of your load. So this is my load. Okay. All right. So your source impedance is in kilo ohms and your load impedance is in ohms. Okay. Due to which what happens is that the power delivery won't be that good. Example. Okay. I'll tell you. Okay, this is your source Vs. Okay, and this is your source impedance Z0. Okay, say for example RC. Okay, and this is your load RL. Okay, what we have taken 32 ohms we have taken. Okay, let's say RC is equal to 1 kilo ohm, and let us take voltage as Vs is equal to, let's say, some say 1 volt. Okay, this is just for example's sake I'm taking. Okay, and due to which say current I flow. So figure A represents non-impedance matching case. I'm considering non-impedance matching case. You can clearly observe, right? This is 1 kilo ohm and this is 32 kilo ohm. So there is a huge difference in ohmic value. So that's called as non-impedance. Impedance mismatch. All right, so let's find out I. So when I find out I, where 1 volt represents the RMS value, okay, of course, RMS value, then only we can find out the RMS value of current. Okay, so I is equal to basically V divided by RL plus Z0. So 1 volt divided by 1 kilo plus 32. Okay, so roughly how much do we get? It's about 9.68. Okay, 9.68 into 10 to the power minus 4 amperes. Okay, so therefore power PL, okay, that is power delivered to the load, power PL is equal to IL square, okay, into RL. Okay, so this itself is IL, right, because it's a series circuit. So it is basically 9.68 into 10 to the power minus 4 square RL. Okay, So RL is 32 ohms. So it's about, 3 into 10 to the power minus 5 watts. Okay. So this is the power being delivered to the load if there is impedance mismatch. Okay. Now let us consider the case, okay, wherein your RS is equal to RL, okay, which is equal to say 32 ohm. Okay. So by introducing some circuit, okay, some circuit between load and amplifier, we have achieved this particular condition. What is it? RS, okay, sorry, yeah. So this, okay, I have taken Z0, right? Okay, let me take it as Z0 itself. Okay, Z0 is equal to RL is equal to 32 ohm. Okay, so that means to say what I have done over here is that I have my amplifier. Between amplifier and the load, okay, this is my load, which is 32 ohm. What I have done, I have connected a two-port network. Okay, two-port network, such as emitter follower. So due to which, what I am trying to achieve is that my earlier output impedance of the amplifier was in kilos of ohms. Okay, due to the insertion of emitter follower, this output impedance, say Z0, has become, very close to RL. Okay, very close to RL. So this RL, sorry, this Z0 dash, now it is going to match with this particular, load. Okay, due to which, you can redraw the emitter follower, sorry, equivalent circuit with Vs is equal to 1 volt. Okay, and this is your Z0 dash, which has become 32 ohms due to the insertion of emitter follower. Okay, that means to say it alters the output impedance. We will see in detailed analysis. Okay, and this is your RL 32 ohm. Okay, now you calculate IL. IL is equal to 1 divided by 32 plus 32. Okay, and then you can find out PL. PL is equal to IL square into RL. Okay, so 1 divided by 64. Okay. It is 15.625 milli. Okay, and IL square into RL is 15.625 milli into load resistor 32. So that gives the power PL is equal to 7.81 milliwatts. Okay, milliwatts. So you can see clearly that power delivery during impedance mismatch case is just 3 into 10 to the power minus 5 watts. On the other hand, with the insertion of impedance matching device such as an emitter follower circuit, the maximum power delivery to the load we have increased to 7.81 milliwatts. So the end node going to be like this: emitter follower helps in impedance matching, which is very, very essential for any audio amplifier circuit. Okay, you won't find any amplifier circuit without an impedance matching device. You have to use impedance matching because all audio amplifier output impedance will be in the range of several hundreds of ohms to few kilo ohms. On the other hand, your speaker impedance or your headphone impedance, earphone impedance is always in the range of few tens of ohms, typically 16 ohm to 32 ohm. All right, fine. I'll stop my class over here. Okay. In the next class, let us look at the detailed analysis of emitter follower. Okay. Let me stop the recording.